All right, so we left off in studying our unions and intersections and the fact that things are mutually exclusive. So what I'm going to show now is some examples here. So if we have a Venn diagram showing the set A, which the sum of the outcomes of a roll of die is even, and B being the sums of 6 or 7, this is what it would look like when drawn on a Venn diagram. So if you roll 2 die, the smallest set of numbers you can get is 1 and a 1, and the largest is a 6 and a 6. So you're going to get numbers between 1 and 12. So evens 2, 4, 6, 8, 10, and 12. And then your odds would start out with 3 and go through 11, of course. We're not talking about the odds, we're talking about the evens and just that the sum is 6 or 7. So what you'll notice here is the set A within its borders, so let me draw it over here, the set A within its borders contains 2 and 4, 4 and 6 and 8 and 10 and 12. And I need to erase this so it looks like a 4 and not some funky 7 or something. So we have that 2, 4, 6, 8, and 10. And then what you'll see is that when set B is drawn, set B encompasses that 6, but it also has 7 in it. So if I were to erase out the set A here, just pretend that it wasn't here for a second, right? Then you see that set B has the 6 and 7 in it. But the overlap containing that 6 is what's shown here. So when we say the union of A, B, C, or A and B, what we're looking at is really just erasing out this right here, this overlap. So I'm not really seeing the overlap, right? I'm just seeing what's in the two sets, just like I was showing before. And this is what's in both of them, and that's the 2, 4, 6, 8, 10, 12, and the 7. And that's what you see in my union here. Now let's go down and let's take a look at the intersection of these two. So we have the same two sets, right? And then the intersection. And in the intersection, what I'm interested in is the completion of these two circles and what's in both of them at the same time. And what's in both of them at the same time is the 6. So A union B versus A intersect B. Now, if two sets are disjoint or mutually exclusive, like we were seeing with A and C before, then they're going to have mutually exclusive they're going to have a null set for their intersection. So here's an example where we see that intersection being a null set. So if we look at the outcomes of our pairs of dice as being our universe, and we look at all the sums that are even, 2, 4, 6, 8, 10, and 12, and we look at all of our sums that are odd, 3, 5, 7, 9, and 11, you see that sets A and D are mutually exclusive of one another. In other words, the overlap, there is no overlap, is a null set. Now, one of the other things that is interesting about this is when we have two sets that are mutually exclusive, there's this thing called a complement. Now, in set theory in particular, we talk about A and A complement as this notation. So this is set A, and this is what we call the complement of set A. Now, this is not like a compliment that you pay to someone, which, oh, your eyes are so pretty, or your hair is so lovely, or whatever. That this one has an E here. So this bar over the top means complement. And when we have mutually exclusive sets, the set itself plus its complement is always equal to the entire universe. And this one represents the universe. And that is the idea that we get from probability, which will be very important to us in terms of finding probabilities for complements. So A complement is equal to 1 minus A. And this will come up in probabilities because the probability of the complement occurring is 1 minus the probability of A occurring. And we'll see that happen over and over. And this, again, will have something to do with being mutually exclusive, or having events that in probability we'll call being independent. And independent is that idea of being mutually exclusive or having no overlap whatsoever. And of course, when they do have overlap, then we don't have direct direct complements of one another, we have to be concerned with this little piece of overlap. And so that'll change the types of probability that we find, or how we find probabilities with those. Now, the last thing here is something about a difference. And the difference really is talking about this overlap. And so I tend to not do this anymore, so I'm just going to go ahead and skip this. I really should take it out of my notes since I really don't cover it these days. Now the next thing here that we have is just this idea of complement. Now, I do want to warn you that some books don't use this idea of complement, and Brace is one of those. Instead of using the bar like we do in set theory, they use a little superscript of a C. I think it's probably easier to typeset that superscript than it is to typeset this bar over the top of it. So just a little warning there. And then looking here at this example, we have a universe of being men and women, and A and B being two different sets, and A being the set of men and B being the set of women. If we were to do this as a Venn diagram, this would be our universe, right? And that would be basically people, right? The human race. And then we have the set A here, which represents our men, and we have the set B, which represents our women over here. And that would be two mutually exclusive sets. So that wraps up the introduction to probability. So I'm going to go ahead and end this video, and then I'll just start in on the sections of Chapter 4 for Triola's book after that.